Alright, so the first couple of videos are going to be a review of things you've seen in, well, a little bit in Math 125 and then in Math 126, or wherever you learned how to do single and double integrals. And then we're going to go into more difficult applications of that. So back in 125, or wherever you learned how to do single variable integrals, you had an x and a y axis, you had a curve, some curve, and you wanted to go, let's say, from A to B, and you wanted to find the area under the curve. So all this highlighted area. And what we did is we used what we call Riemann integration. We divided this area into small slits, which were approximated by rectangles, and the width of each of these rectangles was some small amount dx, very, very small amount. We let that go as small as we can in calculus, and then the height of the rectangle was the value y, because that point is just x comma y, or sometimes we said x comma f of x. So then what was the area? Well, it was the sum. Integral is just a fancy symbol for sum from A to B, and we wanted to add up the area of each of these little rectangles. So that was the width times the height, or this way, the width times the height. And then we do some fancy math to figure out that the antiderivative actually helps us calculate the integral, and then we have the fundamental theorem of calculus and so on. But there is a single integral to find the area under a curve. Now, double integrals, in Math 126, you've seen this, can be used to find the volume under a surface. And we'll just do the most general thing for now. We're just going to take a small chunk of space, we're going to call it dA, and then we're going to have some surface going over it, and then we're just going to take that chunk and go all the way up, so we'll make a kind of prism thing. I don't know what shape this is. It could be a circle, could be a square, could be anything. But I do know how to find the volume of a prism. It's just the area of the base, which is dA, A for area, D for small, times the height, which this function is going to be z equals f of x comma y, right? So that point is x comma y comma z. So integral of, should be writing in black, f of x comma y dA, and there's going to be two integrals, y because a is a complicated thing. It changes in two parameters instead of one. Instead of dividing the number line up into little segments, I'm dividing the whole plane up into, I don't know what shape. Okay, well maybe now I do know what shape. What's the most convenient shape? Probably rectangles. Probably what I'm going to do is I'm going to cut the x direction up into very little tiny intervals and the y direction up into very little tiny intervals. And then my dA is probably going to be this rectangle with length dx and width dy, and then I'm going to go up to my surface, and this is going to be a sort of rectangular-ish thing. But if I really go small enough, it is a rectangular-ish thing. R for region. So I was taking my integral over the region, dA, or I can take, whatever my x bounds are, A to B, and then whatever my y bounds are, C to D, and then I can take f of x, y, and dA. My area, my little area, is now dx times dy, because that's just the area of a rectangle. So I now have my integral. Okay, so for example, let's just do a very easy example. We're going to integrate, let me actually tell you what the function is first. F of x comma y equals xy. On the region, we're going to just take the unit square. 0, 1, cross 0, 1. So what does that look like? You may not need to draw a picture of a rectangle, but in general, certainly for things that are not rectangles, you might want to draw the region. So that's the unit square, 0, 1 to 0, 1. Okay, so how do we integrate that? Well, x goes from 0 to 1 and y goes from 0 to 1. And we'll just have x, y, dx, dy. In this case, it may not matter too much because it's symmetrical in x and y, but remember the inner variable goes with the inner bounds, and the outer variable goes with the outer bounds. So what do I do? Well, remember, just like partial derivatives, which you should also review if you don't remember, I'm going to hold the other variable constant while I integrate with respect to the variable that I'm working on. So I'm doing the inside integral. I'm holding y constant. I'm leaving all this stuff out here. Y is a constant. I'm integrating with respect to x, so it's x squared over 2. Leave y there. 0 to 1. I could write 0 to 1. I'm actually going to write x equals 0 to x equals 1. That notation is optional. I just write it to make sure I don't plug in for the wrong variable. And then I leave all this out here still. I'm going to plug in 1 for x, leaving y over 2, minus plugging in 0 for x gives me 0, so I won't write that part, dy. Okay, now I just have a regular one variable integral, which is easy at this point, y squared over 4. Now I don't need to write y equals because I only have one variable left, and that's 1/4 minus 0, which is just 1/4. And then let's look at a picture of this. So what are we doing? We are, this is the curve, by the way. This is z equals f of xy equals xy. Okay, so what did we just do? We took the unit square, which I've rotated and maybe reflected my axes a little bit. So I guess not reflected, just rotated. So the unit square, which now looks like a rhombus-ish thing, from 0 to 1. And then I've gone up to my surface. Let's see if I can draw this. So all of these go up. Oh, I guess actually the surface does stay on the axes, right? Z equals 0 if either x or y is 0. So none of these go up. It only goes up off of the axis. Okay, so what do I have? I have this weird, this shape then. I found the volume in there, is what I've done. And let's see if we believe it. Well, if I took the whole volume of the cube, so this is the point 1, comma 1, comma 1, which is certainly on the surface. If I plug in 1 and 1 for x and y, I certainly get 1 for z. If I took this whole cube, see if I can draw the cube. Okay, this is not terrible. Something went wrong. This isn't tall enough, is what it is. Okay, cool. If I took that whole cube, volume of that should be 1, right? Because it's 1 by 1 by 1. So volume of this red thing is contained in there, and we've said over here that it's 1/4. So yeah, I believe that. Certainly believe that. You may remember this from 126. Hopefully you at least did one problem with this curve. This was the saddle, where you had one way was concave up, the other way was concave down. So if you did a double derivative test at 0, 0, it was inconclusive. That's what this looks like. Cool. All right, easy example. There'll be more complicated examples in the next video.